In this presentation, we'll talk about the everlasting exponential and its very special relationship with the convolution integral. In a previous presentation, we introduced the everlasting exponential, e to the st, and you recall that this is a signal that is non-zero for all time, so it's everlasting, as opposed to the causal exponential, which is e to the st u of t. Also recall that s in the everlasting exponential is a complex number. Let's look at the response of a linear time-invariant continuous time system with impulse response h of t if we put in an input that is the everlasting exponential, e to the st. Now the initial conditions here are 0, and so we'll find the response to just the input itself, and that response will be y of t is h of t convolved with e to the st. And of course, if we look at what the definition of the convolution integral is, this is the integral from minus infinity to infinity of h of tau, e to the s t minus tau d tau. Now we'll take the term e to the s t minus tau and we'll write it as e to the minus s tau e to the st. And then we'll note that e to the st is not dependent upon tau and therefore can be pulled out of the integral. And then we have y of t is equal to e to the st integral from minus infinity to infinity h of tau e to the minus s tau d tau. This result is repeated here at the top of the page. And at first you might not think this is very interesting, but actually what it's saying is quite important. It says y of t is e to the st multiplied by a constant, because the integral from minus infinity to infinity of h of tau e to the minus s tau d tau is just a number. In fact, it's a complex number. Now this number will depend upon what value of s we're using in the integral, and so we can think of this as a function of s, and we denote it h of s. So h of s is equal to the integral from minus infinity to infinity of h of tau e to the minus s tau d tau. Now one thing we haven't discussed so far is the convergence of this integral, and that's something we'll have to return to later. So in the case of an everlasting exponential input, we find the output y of t is this number h of s times e to the st. So you see the input, it has the form e to the st, but so does the output. This is the key point. Usually when we put an input in, the output will not look like the input. It will have some other functional form. But for this particular input, the output has the same form. And so e to the st is often referred to as an eigenfunction or a characteristic function of the linear system. H of s has a special name. It's called the transfer function of the system, and this will end up being a term we'll use again and again, especially after we introduce the Laplace transform. So one way of thinking about the transfer function is it's the ratio of the output signal over the input signal when the input is e to the st. Now it should be pointed out that transfer functions exist only for linear time-invariant continuous time systems. Nonlinear systems, time-varying systems, they do not have transfer functions. So we have to restrict ourselves to the subclass of linear time-invariant continuous time systems if we want to talk about transfer functions. Another important point is that the input here is the everlasting exponential, not the causal exponential. So we make a distinction, if you recall, between e to the st, which is everlasting, and the causal exponential e to the st u of t, which is 0 for t less than 0. Here is a very simple, yet very important result. And that is, if we have a system described by the differential equation q of d times y of t equals p of d times x of t, then the transfer function of this system is given as h of s equals p of s over q of s. That is, we simply need to replace the differential operator d in q and p by s, and then take the ratio of p of s over q of s. So finding the transfer function of a system described by a linear time-invariant differential equation is quite easy. Now, this is a strong result, but it's not hard to show at all. All we need to do is take x of t equals e to the st and put that into the differential equation, then solve for y of t, and then take the ratio of this output signal to the input signal, e to the st, and that will give us h of s equals p of s over q of s. So here's how I'd like you to think about our linear time invariant system. It has an input, x of t, which goes into the system, and the output is y of t. And the relationship between the input and the output is governed by this transfer function, h of s. This picture is what's referred to as a block diagram of the system, showing the inputs and the outputs, and the transfer function that relates them. Let's do a quick example problem. And this example is a mass on a spring. And we have an input force, which we'll label x of t, and an output displacement labeled y of t. And the equation of motion is my double dot plus ky equals x, or md squared plus k times y of t equals x of t, where we're now expressing it using the differential operator notation. Our goal is to find the transfer function. So we have q of d is md squared plus k, and p of d equals 1. Now we know to find the transfer function, we simply need to replace the differential operator d by s and take the ratio. So the transfer function h of s is p of s over q of s, which is 1 over ms squared plus k.